Be super happy that this is working, at least for now, so flawlessly. We got Robert from remote in a fireside chat, and he will speak about Erlang, as he's one of the co-creators of the language. And yeah, we have been lucky to be in touch over the past year, not like super intensively, but again and again. And we already received some interesting proposals at the Eternity Crypto Foundation for some research projects, and for sure we will stay in touch and work and do some things in the future too. And today he joins us remote and presents a little bit about Erlang, and I think this gives also a nice insight to why we are using it in our core protocol. So the stage is yours, Robert.
Okay, thank you. So I just want to warn you, this is the first time I'm giving a presentation remote, so we'll see how it goes. Yeah, so this is about Erlang. I think the best way to describe why it looks like it does, because it looks a bit different from most other languages, is a bit about history. They're meant to be very short, so don't worry. It started off with, well, it comes from Ericsson, although it's not a telecoms language as such, but we were working in the Ericsson's computer science lab, and they had a switch, the AXE, which was very successful, but it was difficult to maintain, to develop and maintain. And the problem we were trying to attack was, how can we make that easier to do that, more efficient to do it? We had our own small switch in the lab, which we were experimenting with. So we tested many different types of systems and did a lot of experiments, making the switch ring and doing real, so I'd say real telecoms. One of the things we found after a while was what was the actual problem domain. It wasn't controlling the switch because someone had written that code, so we could just send commands to it and do it. We found things like there's a lot of concurrency going on. There were a lot of timing constraints. Things had to happen at a certain time, which meant, for example, the system could never block. It needed to be distributed for fault tolerance, continuous operations, and maintenance while the system was running, and it had to be very fault tolerant over time, so both for hardware and software failures. So these were some of the main points. These were the main difficulties, not controlling the switch itself. And if you look at this is not just telecoms. There's nothing telecom specific in these problems we were looking at. The telecom bit someone else has solved. We were looking at the system. So Erlang and the system around it, how it was meant to be used, was designed to solve this type of problem. And Erlang OTP provides direct support for these type of issues. That this is what it was all about. Some things we felt here, well, later reflections of, we were not out to implement a functional language. This was not our goal. It became functional as it went along. It started off being logic and it became functional. We were not out to implement the actor model. We heard later that we had implemented the actor model, but at the time we did not know about the actor model. We were just trying to solve the problem. We had these set of criteria in the problem which we had to solve to make the system interesting at all. If we couldn't solve the problem, it wasn't interesting. This made development of the language and the system very focused. If we came up with a new idea, would it help to solve the problem? Yes or no. If it was useful, then we could keep it. If it wasn't useful, then we would get rid of it. And we came up with quite a number of ideas we thought were fantastic. We just found out they just weren't useful, so they didn't get into the system. And again, the language and the system, the language itself and the system properties and how users to build things, they evolved to solve the problem. This was the main goal. So where do we end up with? Well, we end up with, you need lightweight concurrency. There are a lot of things going on in a switch. There might be large switch, might be tens of thousands of calls, maybe hundreds of thousands of users, things going on. So you need a lot of concurrency, which meant everything around processes, creation, context switching, communication had to be very cheap and fast. Everything was based on asynchronous communication. This was easiest to do and also required for the problem. We need to have process isolation. When things go wrong and a process crashes, it must not affect other processes. We need support for doing error handling and support for doing continuous evolution of the system. And again, had to be soft, real-time, non-blocking. So it was a real-time system, but if you occasionally missed the real-time, it wasn't too bad, but you were not allowed to block. We also discovered after our experiments, we need some form of high-level language to get real benefits. Remember this, we're talking now late 80s, right? So Ada was considered a higher level language. The system should be simple. The language itself should be simple. So simple in the sense, you know, a small number of basic principles that the base for everything. And if you get these right, then the language will be powerful, but it'll be easy to comprehend and good, right? So small in this case is good. And the language should be simple to understand and program. Now we also, simplicity is difficult, right? Building complex systems is easy. You just chuck in new things every time something occurs. If making something simple, you have to plan about it. And Dijkstra has a number of quotes on it. And one I like, it really is, simplicity is a great virtue, but it requires hard work to achieve it and education to appreciate it. And to make matters worse, complexity sells better. Yeah, if you spend a year devising a system which is very simple in the end, your client might be very happy about that. We also found they should provide tools for building the system, not solutions. We tried a number of times to make solutions, but we usually got it wrong. So it's much better providing the basic tools and letting the people building the systems come up with the solutions. As I mentioned before, we had a small lab. We had a small switch in our lab which we experimented with. It's the small one standing behind the computer I was working with. That's me 20 years, 30 years ago. I was not just playing here. So we were going to a trade show going to show Erlang, and we thought having that small switch with no blinking lights and nothing to attract people wouldn't be very good. So we thought, well, okay, would we use Erlang to control the electrical train set? Which we did. It wasn't quite the track we had there, but another one. And I admit I went slightly overboard, so I ended up developing a complete automatic train control system for running the system, but it worked and it showed Erlang very well. So where did we end up? So we have a sequential language. It's a simple functional language. Nothing really strange about sequential Erlang. It's got typical features of functional languages. It's immutable data, immutable variables, pattern matching, typically no loops, but recursion rules. The main differences might be it's dynamically typed, and there are no user-defined data types. This had very much to do with the code loading, dynamic code handling. Concurrency, well, here are a lot of the criteria we saw before. We want lightweight, isolated processes. We want to be able to run millions of processes, and there are systems today, live serious systems that do that. We have asynchronous message passing. It's the only method of communication, and this is what you need you need this as the base for building non-blocking systems. If you have synchronous communication, it is extremely easy to block a system. And they're very cheap. We have a selective receive mechanism. This is very nice because it allows you to focus on the messages that are interesting just now and leave the other ones till later. There is no global data. That's it. Well, this has been slightly modified in later versions of Erlang, or the recent versions, version 22, but it is very restricted global data, and in some ways it doesn't behave as global data. So that's the sequential and the concurrency primitives. The basic premise for the error handling is that you will always get errors. You will never get rid of errors. You will always have errors. Just accept the fact. And the basic goal for the error handling mechanism is the system itself must never go down. So when you get errors, parts may crash and burn, but the system must never go down. You also want to avoid writing error checking code everywhere. If you've ever done this, you'll find it becomes extremely tedious and it's extremely easy to get it wrong. So we just want to let things crash. When a process goes wrong, let it crash. The rest of the system will know what to do when that process crashes and keep on going, restart it, or whatever it might be. So that gets us to OTP. So now we'll in this talk, I'm still working bottom up. So we started the basic premises for the language. We've looked at the basic what's in the virtual machine, and now we're looking at OTP. And OTP stands for Open Telecom Platform. But it's a set of design patterns for building concurrent fault-tolerant systems. These are the basic ideas we had when we were designing the language. So the language design together with how you would build a system. So these are based on the ideas, and the basic mechanism is something we call the generic behavior. It implements a design pattern, and it's extensible. The OTP is extensible to allow new patterns, new behaviors. It contains a set of libraries, and there are a lot of support tools for building systems and releases as well, of course. And the interesting thing here is there's nothing about telecom in OTP. So Erlang's not a telecom language, OTP is not a telecom system as well. It's just a politically correct name, you might say. And the thing with building Erlang systems is you find they tend to be very operating system-like. There's very seldom a central thread of execution. There is typically, you will have multiple things running at the same time. The most central thing might be something which just starts tasks and keeps track of it. So you might have an Erlang system which is looking, say, at connections, at internet connections. You might be running hundreds of thousands of internet connections at the same time, each one doing different things and managing. This is very common in the systems. So now we've gone up a bit, now we'll go down and look at the beam. So what is it? It's a virtual machine to run Erlang. That's really all it is. It's the main virtual machine that's used to implement Erlang. And if we look at the properties of the beam, we see it contains direct support for all the things we wanted in the language and in the system. So it has support for lightweight massive concurrency. It implements it, in fact. It supports asynchronous communication, process isolation, error handling, continuous evolution of the system. This means dynamic code handling, all the support, what's all in there. The soft real-timeness, the non-blocking, there's a preemptive scheduler. It is extremely difficult to block the beam. You can do it, but you really have to put a lot of effort into doing it because the beam puts a lot of effort into making sure you can't do it. There's transparent multi-core support. Built-in load balancing system. I don't have to think about this. There are powerful introspection and internal tracing primitives for looking at the system while it's running, and a number of interfaces to the outside world. If you're looking more at the language level, there's direct support for all the things you'll find in typical function languages, like immutable data. There's a predefined set of data types. I can say, by the way, immutable data, it's immutable all the way down. This is not a language feature. This is built into the virtual machine. There's support for pattern matching, functional languages, model handling modules and code. And again, there is no global data. So that gets us to what we call the Erlang ecosystem. And what is it? Well, it's a set of languages built on top of the beam, on top of Erlang, on top of OTP. And well, this is the logo for it, you might say. And of course, there's Erlang there and a number of other languages. I'll mention a few of these. The thing here is, these languages, these implementations of the languages, they follow the rules and work in the right way. They can openly interact and support each other, which means you can have mixtures of systems running this, which you do today. I mean, it means the whole system can be more powerful than any specific language. So yeah, how about extending the system? So I've been talking now about Erlang and OTP. What happens if you want to add more? Well, this is like you have the old ceremony, you want to add a new skin to it. This, by the way, this Leonard Cohen CD is very good. It's depressing as Leonard Cohen always is, but the music's extremely good if you want to listen to it. So yeah, I call it 3 different ways of doing this. So I say what I call here is native languages, and they're the ones that keep the basic Erlang execution model and data type. They're sort of Erlang at the bottom, and they might give you a new syntax. They might provide new different packaging and tools and things like this for it, but the basic level is still Erlang. And there are a number of these today. So we have, well, Elixir is a very big one. I'll mention a little bit about that later. LFE, it's a Lisp. I did it. I love it. There are a number of statically typed functional languages that are being developed, and a few others as well too. And I would say the biggest of the other languages, of course, is Elixir. And again, what they say, it's a dynamic functional language designed for building scalable and maintainable applications. Well, that's what we do. Right? It's influenced by Ruby, but it's not Ruby. It's not Ruby on the Erlang VM. So you have to be very aware of this when it has metaprogramming capabilities using macros. It has a lot of libraries, and a lot of the libraries and interfaces have been standardized, many rewritten, and there's a lot of extensions for them. They could do something we could not do. We could not go through and rework our standard libraries because that would crash too many systems. So people would quite rightly complain that the libraries, say, weren't very consistent. But when we came along and said, okay, we'll fix it, we'll change it for you, then they'd say, no, you can't do that because then our system won't work anymore. Elixir could do this when they developed the language because they were coming with something. And of course, for those who use it, I know there's a group in Eternity who are using this. There's an extensive set of build tools and a lot of packages for doing this. So it's a skin, but in some ways it's a thin skin, and in some ways it's a very, very thick skin here, we say, with the two build tools and the packages. But at the bottom level, it has the same basic semantics as Erlang does, the same style of modules and functions, which means it's very easy to interface Erlang and Elixir. So Elixir can call Erlang, and Erlang can quite easily call Elixir. Yeah, LFE, this is my favorite. I like Lisp. This was my first high-level language, so I like Lisp. And it's a Lisp syntax front end to Erlang. So it's a real Lisp. It's really high homoiconic, and it's got real macros. Macros the way God intended. But it wasn't. We're not doing a standard Lisp or a scheme, because they would not fit directly onto the Erlang system. They have, for example, mutable data and other ways of working with modules. So the Lisp has been modified to fit these. So, for example, there is no mutable data. And we have standard Erlang data types, Erlang style modules and functions, macros at compile time. It's a Lisp 2 instead of a Lisp 1. I'll not get into that discussion now here, but yeah. There are also a number of attempts being work in progress now about building statically typed functional languages on top of the Erlang system, building. And two here are Gleam and Alpaca. And there's work is being done on these. This, in some ways, it's easy to do this. In some ways, it's difficult. So you can set up your statically typed system. You can make your set of modules and packages which are statically typed and fit everything in, but you still have the problem of interfacing the outside world, which means that you're suddenly running into dynamic typing. So the problem is not trivial. The work is being done on this. So that's why I say native languages, because you're keeping the same basic Erlang structure. The other one we're looking at, we go down another level here, is I call them non-native languages. So we're languages running on top of Erlang, implemented in Erlang, but don't have the same Erlang execution model. And I'm just going to mention two here, which I have done myself, so I know what's going on here. So there's the implementation of Lua and an implementation of Prolog. And they are very different language semantically and how they handle data from Erlang. So, for example, Lua, it has shared global mutable data, everything we don't do in Erlang, for example, but that's what Lua does. Prolog, for example, has a completely different execution model. So you can implement these on top of Erlang, but then you're getting away from the Erlang execution model. That's why I call them non-native. But these work very well, and they sort of have their place in the system. The third level I call extending the system, I call external systems. That is, well, a number of different things you want to do here. You want to talk with other things, other processes in the operating system which aren't running Erlang. We have a concept called ports for doing that for it. Maybe you want to include code in your Erlang system not written in Erlang. So we have something called NIFs for natively implemented functions, and it allows you to write code in C and call it from Erlang as if it was Erlang. This is very useful for it. There's also support for threads in it. And this feature is actively used inside the aeternity system. So we have, for example, C code, which is doing encryption and compaction and databases and things like this for it. They're written in C and they're called from Erlang. C node is it's a bit in between in that we have external nodes written in other languages that look like distributed Erlang nodes. So we can send messages to processes on them and get messages back. It's quite a nice interface for it. There are a couple of work in there. There's also work in progress looking at Rust and assembly. So this is a little bit about the Erlang system and different levels for it. Erlang is one of those languages that you don't see it, but you're using it everywhere. And there are very few, so there are very many systems written in Erlang which you'll find in everyday use, but people don't know about. So, I mean, there are a number of tools like RabbitMQ, for example, is written in Erlang. And I'm guessing most RabbitMQ users don't know or don't care about that. The React database, again, is written in Erlang. It's the same thing there. eJabberD, CouchDB is written in Erlang. So there are a number of these standard tools that are written in Erlang for using the Erlang features. I mean, React is the way for doing distributed data with a set of features. It's also used in a number of very widely spread products, you might say. So, of course, the big one is WhatsApp. All the WhatsApp servers, the back-end servers, are written in Erlang. And they are processing, what, about 1 billion users? They're also the ones who are seriously running. They have one of their back-end servers. It can be one Erlang system, running on one machine, which might be processing millions of concurrent connections, TCP connections coming in at the same time for it. So they are literally using millions of processes in their system. Bet365, part of their system, is written in Erlang, and they advertise themselves as the largest online betting company in the world, right? And part of their system is written in Erlang. Ericsson use it. Part of their systems are written in Erlang. So if you're sending mobile data over your phones, you're probably running through Erlang systems. Klarna use it. The banking use it. OTP Bank, a Hungarian bank, they have their back-end servers written in Erlang. Aeternity, of course, where you're representing, part of that system is written in Erlang as well too. So it is very widely spread, although it's something that you often don't see. Cisco servers have Erlang inside them. And how many million Cisco servers are there in the world? So it's there. It's spreading even more now. I mean, Elixir has opened up a complete new set of companies that are interested in using it for it. So it's spreading a lot there as well too. And yeah, that was about all I wanted. Well, I could say I can keep on talking for as long as I never stop, but I think that's about enough here. I don't know if we can manage any form of questions or anything like this, but
I think we can.
People
Thank you
Yeah,
very
we
much
can.
for
Yeah.
this
Thank you. Right. So, who wants to ask a question? Okay, we have a lot of questions. Let's do one. Let's start from here.
Okay. As I know, the very first implementation of Erlang was done in Prolog, right?
Wait.
Oh, okay. Oh, that's you.
It's Elton John in disguise.
that was me. That was my fault. That was my fault. Okay. Okay. Yeah.
Okay, so can you hear me?
Yeah, you need to hear the mic.
Yes?
But
Okay. As I heard, the first implementation of Erlang was done in Prolog. And I see a lot of inspirations taken from it in Erlang. So my question is, what was the motivation of such a move? I mean, why did you choose such an exotic, I would say, language to be a parent of Erlang?
Yeah, so why Prolog? Okay, so as I said, we were experimenting in the lab with many different languages and systems. I think we must have done 30 or 40 different experiments running telecoms, amongst other things using Prolog. And I remember Joe Armstrong, one of the three, the first of the three actually, he'd written down a set of rules for telecoms or telephone calls. And another person came by and said, oh, that looks like Prolog. And then Joe started looking at Prolog and he said, yes, it does, doesn't it? So then he did a first implementation of evaluating these rules in Prolog. And we could connect up our switch to it so we could actually control it. And then, of course, you found that worked well for one call, but if we wanted multiple calls, which of course we do, then you had to start adding concurrency to it. So now we started building a sort of little engine in Prolog for running out Prolog rules, which means you could run multiple rules. And the same thing with error handling and stuff like that for it. And then after a while, we found that for the requirement things, how we wanted it to work, Prolog wasn't quite right. So that's when it started migrating from a logic language to a functional language, and we ended up in a functional language. That's why, because we just found it fitted us better, what we wanted and how we want to do it. But that's why we started it with it. Is that?
yeah, I think we have another one. Yeah, and that's it, I think. Let's take one more.
Yeah, by the way.
Hi, thanks for the inspirational presentation. So my question is about the data types. So you mentioned that that was one of your requirement to not this is how I got it, to not have the user-defined types, custom types, or abstract data types. What was the motivation for that? Why you made such a decision?
So that was no user-defined data types. Yeah, okay. That came a lot from our need to be able to dynamically load code or load code at runtime, which means you could, having user-defined data types is good, it's nice, but it also means that you need to be able to define them consistently over the whole system, which means it's very difficult, or we found it very difficult then, at least anyway, to be able to upgrade the system while the system is running, because you might load in a new version of the module which does things, uses different data types for it. And you might want to migrate and update things. And we found we could not do that if you allow user-defined data types. So that's why there's only a predefined set of data types for it. It was the dynamic code handling that was the cause for it.
It's a follow-up, I presume. Yeah, go on.
Very quick follow-up. If you would about to design and make this decision again, would you do it the same or not? I mean, would you get rid of the user data types or keep them?
Again, that if I was designing for the same problem and had the same requirements, I'd probably end up with no user-defined data types. Just because well, there may be a way of solving it now, but I don't know of any way of being able to do that, to upgrade data types dynamically in the system for it. That's about all I can say for it. That's just where we ended up being for it. That's why I mentioned one of the problems of doing implementing a statically typed system on top of Erlang, like Gleam or Alpaca. It's in one way it's not difficult to do it, but it's perfectly feasible to do it, but it makes interfacing the outside world quite difficult for it. And if you can accept, for example, that you don't allow updates to parts of the system, you have to update the whole system in one go, then you could add user-defined data types.
Great. Thank you very much, Robert.
Round of applause, I think, for Robert, guys. Come on.
Okay, thank you.
Thank you.